In this part of the data structure course related to stacks and queues, you will learn what are linear and circular queues. We will declare and implement a class for circular queue. A queue is a data structure that stores elements in a list and permits data access only at the two ends of the list. An element is inserted at the rear of the list and deleted from the front of the list. We have front and rear as the two ends of the list. Elements are removed in the same order in which they are stored, and hence a queue provides first in, first out, or first come, first served ordering. In a queue, we have two ends. Front, we get an element from this location, so elements are removed from the front of the queue. Rear is showing the position to add next element at that location. So the elements are inserted at the rear of the queue. Suppose that initially the queue is empty and there is arrival of A. A is inserted at the position where rear shows, and rear is incremented by 1 to show the next position. By the arrival of B, B is inserted at the position shown by rear, and rear is incremented to show the next position. By the arrival of C, C is inserted and rear is incremented to show the next position. When an item is deleted from the queue, then it is taken from the location indexed by front, it is removed. So front is incremented by 1 to show the next element in the queue. Here also there is another deletion from the queue. B is removed from the queue. It is the item in front of the queue. Now front shows the next element. First, we are considering the linear queues. Consider the following operations performed on a queue of size 4. The values of pointers front and rear and the contents of the queue are shown below after each operation. Here the operation is explained. Initially front and rear are set to 0. We have 4 locations in the array of the queue indexed as 0, 1, 2, and 3. And this is the element inserted or removed from the queue. Initially front and rear are 0, queue is empty. First we have an insert operation. The item to be inserted is 12 and it is inserted at the position shown by rear, and rear is incremented by 1. So at location 0 we have 12 and the element on which we are operating was 12. The next operation is insert 15. 15 is inserted at the location rear. Rear was 1 and 15 is inserted at the location 1, and then rear is incremented by 1. Then we have insert 17. Rear was 2, so 17 is inserted at location 2, and rear is incremented. And then we have a delete operation. Delete is applied at the location which is indexed by front. Front was 0, so the item at this location, location 0, is removed from the queue, and front is incremented by 1. So now this is the front element in the queue. The value of the front is 1. There is another delete operation. Front was 1, so 15 is removed from the queue. Front is incremented by 1, so this is the new front element of the queue. There is insert operation here. 10 is inserted at location 3 and rear is incremented by 1. The next operation is insert 5. But notice that there is no more location to insert 5 in the queue. queue is full, so this will result in an error. In fact, there are locations which are empty, but in a linear queue, we are not able to use them. Although there is empty space, it cannot be used, so a better representation is needed. Circular queues are used to solve this problem. For a more efficient queue representation, consider the array to be circular. We have data members, front, rear, and count, which are initialized to 0. The array is starting with location 0, 1, 2, 3 up to n-1, and because we are assuming that the queue is circular, we are assuming that after n-1, the location 0 comes. There are n locations in the queue, 0, 1 up to n-1, and count 0 corresponds to the case the queue is empty. Initially, front is equal to rear, and they are both equal to 0. We insert a new element at the location pointed by rear, and then we update the rear pointer to point to the next available location. As we insert elements, rear becomes rear plus 1. However, if we insert an element when rear is equal to n-1, rear becomes 0. So if rear is 1, it becomes 2, or if it was 2, it becomes 3. However, if it was n-1, then it becomes 0 after the insert operation. The front pointer changes similarly. Now consider the case, front is 0 and rear is n-1 and count is n-1. That is, there are n-1 elements in the queue. If we insert another element, queue becomes full and rear and front becomes 0. They are the same and they are 0. And count is n. Therefore, in both cases, whether the queue is empty or full, we have rear equal to front. The cases the queue is empty or full are discriminated by the value of count. By using only front and rear, we cannot discriminate empty and full cases. One way to overcome this problem is using only n-1 locations of the queue. Then rear equal to front represents the case queue is empty, and rear plus 1 mod n equal to front corresponds to the case queue is full. Another method might be keeping a flag to indicate whether the queue may become full or empty when rear becomes equal to front, or to use count as explained before. In this example, we are using front, rear, and count. They are all initialized 0. Initially, the queue is empty. Then there is an insert operation, insert A. It is inserted at the location pointed by rear, and rear is incremented to show the next location. So rear becomes 1, and also because we have one element, count is incremented, it becomes 1. Then there is an insert operation, insert B. Then it is inserted at the location pointed by rear, and rear is incremented to show the next location. So rear becomes 2, and also count is incremented, count becomes 2 also. Insert C results in inserting C in this location pointed by rear, and rear is incremented by 1, and also count is incremented by 1. So this is the new content of the queue. Now there is a delete operation. The item pointed by front is deleted from the queue. Then front is incremented by 1. It points to the next location. So this one is the new front element of the queue. Here notice that front is incremented by 1. It becomes 1. And count is decremented. It becomes 2. Now we have only 2 elements in the queue. Another delete operation. The item pointed by front is B. It is removed from the queue. front is incremented by 1, it will point to this location, and also the count is decremented by 1. We continue. There is an insert operation. Rear was shown to this location, it is inserted here, and rear is incremented by 1. So in this case, notice that rear was 3 and it becomes 0 because the Q is circular. Then we are inserting E into the Q. It is inserted at this location and rear is incremented by 1. Meanwhile, the value of the count is incremented by 1 as before given here. Continue, there is a delete operation. We have this item in front of the Q. It is removed from the Q and front is incremented by 1. It will point to the next location and count is decremented by 1. So it becomes 2. Another delete operation. The item pointed by front is deleted from the Q. Front is incremented to point the next location. Previously front was 3. When it is incremented, it becomes 0 because the Q is circular. Count is decremented by 1. It becomes 1. One more delete operation. The item here is deleted and front is incremented by 1. Now notice that front and rear are the same. The Q may be full or empty. Because count is 0, we understand that Q is empty. There is an insert operation. Because Q is not full, we can insert it. And it is inserted at the location pointed by rear. And rear is incremented by 1. And also count is incremented by 1. Now we are going to implement the Q in C++. Here is the class declaration. We are including the input-output operations and also include standard library. We are defining max Q size as a constant integer and its value is 50 and the class is defined as a template class. Here we are using data type as the template type. When the class is declared, whatever the type here will be defined. In class Q, we have private part, Q array, and its parameters are private. We have integer front, rear, and count private. We have a list, Q list. Its size is max Q size, declared here. And the items to be stored in the Q list are of type data type. These are the private data members. We have public methods here. We have the constructor having the same name with the class. There is no parameter. This is to initialize data members. In fact, we are setting the value of the front, rear, and count to 0 when the constructor is called. We have Q modification operations. We have Q insert. There is an item to be inserted into the Q of data type. This is defined as a reference and constant for not reserving space for the item when the function is called. We have Q delete. No input is needed. Whatever deleted will be returned from the function, so it is of data type. These are the Q modification operations. We have Q insert to insert an item into the Q. The item is of type data type, and this is a reference and constant reference. This is used for not reserving memory when the function Q insert is called. There is no return type, only the item is to be stored into the Q. The other one is Q delete. There is no parameter, but there is a return object here of data type. Whatever deleted will be returned. The other operation is clear Q. There is no input, there is no output, only we will set front and rear and count such that there will be no more an item in the queue after clear queue operation. We have queue access method, which is data type queue front void constant. This will return the item in the front of the queue, but there is no change in the content of the queue. We have queue test methods, which are to return the number of elements in the queue. That is, this is to return the value of count. This is not changing the content of the queue. It will return the number of elements, that is count, which is integer. The queue empty method checks if the queue is empty, and if it is empty, it returns 1. This is done by comparing the value of count with 0. If count is 0, it means that queue is empty. The other one is queue full, and there is no input again. It will return true if queue is full. And this is done by comparing the value of the count with the max queue size. If they are the same, it means that queue is full and it will return true, otherwise it will return 0. Here's the implementation of the queue class is a template class. We are saying template class data type. This is the constructor. Constructor is the method for the queue class and it has the same name with the class. There is no input value, there is no return value from here. We are setting front, rear, and count to 0 in the implementation. There's nothing else. We have also queue test methods. This is the queue length method on the class of queue of data type. This is a constant method and it will return the value of the count, which is an integer. This is the length of the queue. We are checking if queue is empty by comparing count with 0. If they are equal, it will return 1, otherwise it will return 0. The other method is queue full. It will return an integer. It is checking if count is equal to max queue size. If they are the same, it will return 1, otherwise it will return 0. Now we consider the queue modification operations. Queue insert is to insert an item into the queue. Again, it is implemented as a template method. This is a method for the class queue of data type. Here there is a parameter called item of data type, which is a reference and it is set as a constant for not reserving space in the memory when it is called. It should terminate if queue is full. If queue full, then at the error device we will see queue overflow and next line it exits the program. Otherwise, that is queue is not full, then we continue. Count is incremented by 1. At the position rear of the queue list, the item is stored. Rear is set to rear plus 1, and this is sign for the remainder when divided by max queue size. By this remainder operation, if rear was max queue size minus 1, when it is incremented, then we want it to become 0. It is provided by this remainder operation. The other method is queue delete. Delete element from the front of the queue and return its value. It is implemented again as a template method. It's a method on the queue and we are deleting an item. It is to be returned from the function. Its type is data type. Again, this is a template type. We are defining a temporary variable data type and we are checking if queue is empty. If queue is empty, in that case, we are sending a message to the error device, deleting from an empty queue and line and exit the code. If it is not empty, we continue. We are getting the item at position front of queue list and it is stored into variable temp defined here. Then count is decremented by 1 and front is incremented by 1, and on that remainder by max queue size is applied. So if it was equal to max queue size minus 1, by this incrementation and by the remainder operation, it becomes 0 because we are designing the queue to be circular, and then it returns the value of the temp, which was the front element in the queue. The last one is queue access. The name of the function is queueFront. There is no input for the method. It is not changing the content of the queue, so it's a constant method. It will return data type. It returns the item stored at the front of the queue list.